Welcome back to ECE 320A. We're in Unit 9, which is our transfer function unit, and now we're focusing on hitting that system or a transfer function, hitting that with a sinusoidal signal for an input, and we want to now apply the expression or the formula that we just derived in video number 5 in this unit, which is now finding or working through an electrical circuit to find the sinusoidal steady state output. And in this circuit, we will go ahead and excite that circuit with a signal 5 cosine 2t plus 45 degrees. We want to know what is the sinusoidal steady state output current, where the output current now is the current in the rightmost branch of this RLC circuit. And we have quite a few energy storage devices in this circuit. We have 3 inductors, we have 2 capacitors, we have 5 energy storage devices. So if this particular circuit, generically, we would expect it to be fifth order. We may have some cancellations because of the special way that we've now combined these rightmost branches and their exact values being 1 Henry inductors and 1 farad and a half a farad for the capacitor, and we have a 1 ohm resistor. But now what we want to do is find how is this output current in this rightmost branch going to oscillate if we excite this circuit with a waveform, which is a voltage waveform of 5 cosine of 2t plus a phase shift of 45 degrees. We want to now figure out what is I sub 0 of steady state. And you should already have a understanding as to what is going to happen. After the transients, what do you expect to see I sub 0 of steady state of t looking like as a waveform? Could you simply, if you were now in a job interview, could you write down a generic expression for I sub 0 of steady state of t? Hopefully you could. Hopefully you could pull out a piece of paper, or if they hand you, if your interviewer now hands you a piece of paper, hopefully you can now say, oh, I know that after the transients, which will be gone after 5 time constants, where that time constant now is the associated, let's say, with the dominant pole in this system, my I sub 0 steady state of t is going to be some amplitude. I don't know what it is. Let me just say it's some gamma. But I do know that it will be oscillating at a frequency of 2 radians per second, and I don't know what the angle is going to be. So let me just say that that's some angle. Oh, and I could maybe say, well, it's going to be 45 plus some additional phase shift due to how the system now delays the signal as it progresses through the system. I know that I should expect this structure for my sinusoidal steady state output at that branch, the rightmost branch. What is the current? Now what we need to do is invoke our understanding of circuit analysis to try to figure out how do I find gamma and theta in this particular case. How would you do that? How would you analyze this circuit, and what do you need? How do you find gamma and theta? Hopefully you realize how to start analyzing this circuit, and you could immediately go from this time domain circuit into the S domain circuit. You need the transfer function between this input voltage and this output current. You need to find the transfer function between that input signal V sub I and the output signal I sub O. So we need this transfer function H of S that is equal to I sub 0 of S over V sub I of S. We need that H. We need H of S. And we can find the transfer function by putting this circuit into the frequency domain. How do the resistors come into the S domain? Well, they come in very easily. They're constants. They don't depend on frequency. Those are just one. Now, conveniently enough, our inductors all have the same numerical value, and so they will all look the same in terms of their impedance, and we know the impedance in the S domain of an inductor, that's SL, so all of these are now just going to be S's. The capacitors, okay, I changed things up a little bit. Now we have the impedance of the leftmost capacitor is 1 over SC. So this now becomes 1 over S. And the rightmost capacitor is 1 over SC, where C is now 1/2. So we now have 1 over S times 1/2. That 2 in the denominator can actually jump upstairs so that we now have the impedance of that capacitor is 2 over S, where this is now 1 over SC, and I've simply multiplied by the magic number 1, 2 over 2, to get or obtain 2 over S for that impedance of the second capacitor. Now that I have that, I've now put my circuit in the S domain. Now I can play with algebra, do my circuit analysis with algebra with these complex frequencies S floating around. How do I find I sub 0 of S? Maybe what you will realize is, oh, I have one node that's different from this node, and I've now highlighted that with this red dashed oval. Let me call this node a voltage relative to the ground terminal. Let me call this node V sub 0 of S. So this is now plus V sub 0 of S. That's the voltage across these two parallel combinations of inductor and capacitor. And that's really the only unique voltage that we need other than the applied voltage of our voltage source V sub I. So now in terms of V naught of S, what is I sub 0 of S? Well, that's just Ohm's law in the generalized form. So now we have V naught of S over the impedance in that rightmost branch, which is S, plus 2 over S. So I sub 0 of S, if I can now find V sub 0 of S, I can now say that I sub 0 of S is just V sub 0 of S divided by S plus 2 over S. Now, how do I find V sub 0 of S? Well, now I can simply write one equation. I just have that one unknown V sub 0 of S. V sub I of S, I'm assuming I know, and I'm going to apply a sinusoid there. So now can I find an equation that will allow me to solve for that one unknown, capital V sub 0 of S? And yes, I can by applying KCL at that V sub 0 of S node. I have a current flowing this direction from that node. I have another current flowing this direction, and I have another current flowing down, which is really just the I sub 0 of S current. And what is the green current? From right to left horizontally, that's now the voltage dropped across that combination of impedance, which is a series combination. So the impedance there is S plus 1, and that will divide into the voltage dropped across that impedance from plus to minus across that impedance. And that voltage drop is just V naught minus V sub I. So the green current is now V sub naught of S minus V sub I of S all over S plus 1. What's the blue current? Well, the blue current is similar to the red current, which the red current is just I sub 0 of S. The blue current is V naught of S divided by the impedance in that middle branch or vertical branch on the left. So now we have V naught of S over S plus 1 over S. And finally, color coding this, my rightmost current out of that node, I'm writing KCL at that node, and the sum of the currents out have to sum to 0. The rightmost current is just I sub 0 of S, but I want to write it in terms of V sub 0 because that's the only unknown I want to exist or have unknown in this expression. And now I have my one equation in one unknown, and I can solve that for V sub 0 of S in terms of the known expression V sub I of S. So here I'm going to allow you the pleasure of performing the algebra and solving for not only V sub 0 of S, but once you've found V sub 0 of S, once you have this guy, which is here and here, once you have that, now that goes up into the numerator of your I sub 0 of S expression. That algebra now should lead you to the following transfer function. H sub 1 of S is now I sub 0 of S over V sub I of S. And now, because of some maybe cancellations, we actually have a fourth order transfer function. If we have a fourth order transfer function, we should be expecting 4 poles. How many zeros do we have in this transfer function? Finite zeros. If we look at this, you should see that you have zeros, 1 at the origin, S equal to 0 will cause the numerator to vanish, and you have complex zeros where S squared plus 1 equals 0. So now you have S equal to plus and minus J. So S squared is equal to minus 1. Take the square root of minus 1, that gives you a J, and you have a plus and a minus of that. So you have 3 zeros, finite zeros, 1 at the origin and 2 conjugates at plus and minus J. You could look at another transfer function. You could find a transfer function. So for a given circuit, you can have multiple transfer functions. We could have defined a transfer function between V sub I and V sub 0, and that we might have called H sub 2. That will have exactly the same denominator as we had in H sub 1. So the poles, the natural behavior of our system, is going to be the same. We could have defined I1, where I1, who knows what I said I1 was. I didn't say anything about I1, but let's just say that that was this blue current there. So now I sub 1, the transfer function between V sub I and I sub 1, if we have similar types of cancellations, we will have then the same denominator, the same poles in that transfer function as we had in H sub 2 and H sub 1. So the way that this system naturally wants to move, if we hit it with an impulse, we would see the natural modes of the system, and those are going to arise from the roots of that denominator, that fourth order polynomial. So the poles are the roots of d of s, the values of s that satisfy d of s equal to 0. If you compute those, you have poles at very close to the imaginary axis, minus 0.0151 plus and minus j 1.2, and another set of conjugate complex poles at minus 0.318 plus and minus j 0.573. And I've already said where the zeros are. The zeros in this h sub 1 transfer function are the roots of little n sub 1, and those were at the origin and plus and minus j. If we sketch those, the zeros are the open circles. Those are all on the imaginary axis. The poles, again, we had 2 that were very close to the imaginary axis, but they were living in the complex, in the left side of the complex S-plane. So these roots are stable, which means that they will die out after you begin shaking this system. And which one of those modes is dominant? The dominant modes in this, for ease of talking about one particular node, they're both going to influence the dynamic behavior, but a lot of times let's just concentrate on the ones that are closest to the imaginary axis. This particular e to the minus 0.015 t will determine the dominant behavior of the system dynamic, or the transients. So we'll have to wait 5 of those time constants, and that's going to be a fairly long time because that is now, in electrical terms, that one's very close to the imaginary axis. So now that we have the transfer function, and we know what we're exciting this system with, v sub I of t, we're exciting it at 5 cosine 2t plus 45 degrees. What is I sub 0 of steady state? And we already said what structure that's going to be. And now that we have the transfer function, capital H sub 1 of s, it's a fairly straightforward process to now find I sub 0 in the sinusoidal steady state. How do we do that? Now that we have h of s, now what do? We now want to find the complex number of our transfer function, and what's that complex number determined from? How do we determine it? What we focus on is the frequency of excitation, and we then evaluate that transfer function at, or on, the imaginary axis at that frequency. So we replace s. Everywhere we have an s in h of s, we replace s with j2. Or we can now say we want to find h of j2. And if we do that, then h of j2 for this particular case, this is h sub 1, so I should say h sub 1. H sub 1 of j2 is now j2. There's the s in the numerator. Then we had an s squared. So we have j2 squared plus 1. And downstairs we had 3 times j2 to the 4th plus 2 j2 cubed plus 6 j2 squared plus 3 j2 plus 2. That now we can do the algebra. That will end up giving us a complex number. I hope you see that that's a complex number. If you simplify that, then h sub 1 of j2 becomes minus j6, or minus 6j, and downstairs we end up with, in rectangular form, 26 minus j10. You can now multiply both numerator and denominator by the conjugate of the denominator, 26 plus j10, to rationalize the denominator. That will now become a real number, and you can divide that into minus 6j that's been scaled by 26 plus j10. All of that ends up with a complex number being 0.0773 minus j, and let me clean that 3 up. I'm not happy with that 3. It's 0.0773 minus j 0.201. That's a complex number, and you should just start sketching that. Now you know what that complex number is in the S-plane. It's somewhere over here at 0.077, and it has a imaginary part of minus j.2. So that in terms of a complex number, you could think of it as this magnitude, so the hypotenuse of that right triangle at an angle determined by that particular computation. And if you do that, convert that into a polar form, h sub 1 of j2, and hopefully you can see that that number is going to be close to 0.2 in magnitude. So it ends up being 0.215, and the angle, by sketching it over there, we know that it's a negative angle, and it's actually an angle of minus 69 degrees. That now allows us to immediately write down the time domain expression for the output current after the transients or in the sinusoidal steady state. It's what we excited the system with amplitude-wise, which was 5. We scale that by the magnitude of h sub 1 at J2, which is 0.215. We aren't changing the cosine, that's the cosine, and it was at 2t plus 45 degrees minus theta, which is 69 degrees. And combining the amplitude, now we're right at a gain of about 1, 5 times 0.2, we're at 1.08, cosine of 2t, and combining 45 and minus 69, minus 24 degrees. And that now is the answer. We now have our gamma on the back of an envelope in our job interview. We've now figured out that we have a magnitude of 1, so we've dropped it by a factor of 20%. We've dropped it by a factor of 0.2, or we're at 20% of where we started with our amplitude, and our phase shift now is minus 24 degrees, so we're lagging behind the input sinusoid, which was a cosine waveform. And that's now the process. The hard part was finding the transfer function, evaluating that transfer function at the appropriate frequency. All we have to do is find the appropriate frequency, which is determined by our sinusoidal excitation. That's now just turning the crank, doing some complex algebra. Once we have that number, that magnitude and angle for h sub 1, we can immediately write down the sinusoidal steady state output.